Okay, welcome to our last podcast for gases. So it's the ideal gas law. The nice thing about this law is that the formula is actually found in your data booklet, but there is one part of the formula that's not in your data booklet. So when I get to that, I'll let you know, and please just be aware of how you use it. So before getting started, let's talk a little bit about the difference between a real and an ideal gas. Real gases are how gases behave in real life. Ideal gases are actually fictional, but we look at it in order to I guess, use numbers or a formula to look at gases, but they don't actually exist. It's more hypothetical. So what an ideal gas does is it follows all gas laws perfectly under all conditions, does not condense when cooled, which is, as you know, a lie, assumes that particles have no volume and are not attracted to each other. What this means, kiddos, is that there's no intermolecular forces, which you also know is a lie, but these are the conditions for an ideal gas, and these are the conditions that we look at when we use the ideal gas law formula. Real gases actually don't follow gas laws exactly. They deviate at low temperatures and high pressures. So that what that means is they become less ideal, right, when at low temperatures and high pressures. They do condense to liquid or sometimes solid when cooled or under pressure. Particles are attracted to each other and have volume, right? They take the volume of a container, remember? And they are attracted using or by the use of intermolecular forces. And they behave like an ideal gas at high temperatures and low pressures. They become more ideal at higher pressures and higher temperatures, and lower pressures. They become more ideal. Ideal gases don't become real because they are fake anyways. Okay, also, in an ideal gas, molecules collide like perfectly hard spheres and rebound very quickly after collision, which means that there's no deformation. In real gases, however, the molecules are actually soft and they can be deformed, and intermolecular attractions are important. The process of collision takes a slightly longer time as a result. So in real gases, collisions are slower, they're more realistic. In ideal gases, kind of like billiard balls, I guess. So in 1873, Johann van der Waals, remember the van der Waals forces, hypothesized the existence of attractions between gas molecules to explain deviations from the ideal gas law. General forces of attraction called van der Waals forces include dipole-dipole and London forces. And you all know about dipole-dipole. If a molecule is polar, it has dipole-dipole, and everything has London forces because everything has electrons. Okay? From now on, we're going to be dealing with ideal gases. So then we have the ideal gas law. It describes the interrelationship of pressure, temperature, volume, which is no big deal. A new one is moles, which is the amount of particles in 1 mole. Remember 6.02 times 10 to the 23, and we're actually including moles in this formula. Okay, remember that we already established a relationship with Boyle's law. Volume is inversely proportional to pressure. We've already understood that there's a relationship in Charles' law. Volume is directly proportional to temperature. We also talked about Avogadro's theory. Volume is directly proportional to the chemical amount, or the moles. And that's found that you know that because you balanced an equation, and the coefficients can be seen as the moles, and the coefficients can also be seen as volume. In this case, kiddos, in ideal gas law, volume is in liters always. Okay, not like the gas laws, Charles' law, Boyle's law, combined gas law, where it doesn't matter. There's a P1 and a P2, could be milliliters, could be liters. In ideal gas law, there's only one volume, therefore it has to be in liters. So if we take all of these laws and we make one fancy law, it's the ideal gas law. But we also know that we have this new introduction of something new, which is called R, which is a constant value, and it's the universal gas constant, okay? Basically, this, if I take in atmospheres or in kilopascals, if I fill all this in at STP or SATP, you're going to get an R value. And that R value is necessary for what's going on and what's happening, right? It's necessary for each and every question that you have using the ideal gas law. It does depend on STP or SATP, and it also depends on ATM or KPA, right? Because obviously you have 1 ATM is equal to 101.325 kilopascals, right? And here we have 1 ATM. So obviously these values are going to change. So for using kilopascals, our R value is 8.314. And if we're using atmospheres, our value is 0.821. This is in your data booklet. This value here is not in your data booklet. So you're going to have to memorize it, or you're going to have to convert your atmospheres to kilopascals and then use the 8.314. Make sure you look at the unit of pressure to decide the R value to use. Any idea how we came up with this number? Basically, we just substitute STP or SATP conditions to get your 8.314. In this case, it's STP. Typically, it's STP. These are all STP values. Okay, so we leave it at STP just to not complicate life. But make sure you see if it's atmospheres or kilopascals. And I wouldn't throw a millimeters of mercury in there. That would just be rude. When solving for the ideal gas law, start by listing your variables. If 3 are known out of the 4, obviously you can find the 4th one. Here's an example. What mass of neon gas should be introduced into an evacuated 0.88 liter tube to produce a pressure of 90 kilopascals at 30 degrees Celsius? Okay, so now we're looking for the mass. And you have to write everything down, kiddos. Here's your pressure. 90 kPa. If it's kPa, your R value is going to be 8.314. Your volume is already in liters, so we're good there. And your temperature always has to change to Kelvin. So 30 degrees changes to 303.15 degrees Kelvin. We don't have mass in our formula. However, what we do have is we have number of moles in our formula. So we find the number of moles, and then using molar mass, we convert to mass. Alrighty, so here's our formula, PV equals nRT. We're going to isolate to find number of moles, and we'll notice that the formula changes to PV over RT. We plug everything in, kiddos, 90 kilopascals, 0.88 liters, your 8.314, because it's kilopascals, right? And we have our temperature in Kelvin. We use our calculators to find our answer, which is 0.0314 moles. Here is my molar mass of neon gas, right? This is the molar mass of neon gas. Make sure that the moles cancel out. And you get the answer in grams, which is 0.63 grams. So here's another bit of a practice. A rigid steel cylinder with a volume of 2 liters is filled with nitrogen gas. We may need that, I don't even know, to a final pressure of 20 atm. So now we're using atm, not kPa, at 27 degrees Celsius. How many moles, that's what we're looking for, of nitrogen gas does the cylinder contain? And we know that the volume of the cylinder is 2 liters, which is nice because it's already in liters. I don't have to convert. So let's write everything we know. Pressure is in atm, so now we're using this value, 0.0821. Our volume's already in liters, we're good to go. Temperature, we just have to change to Kelvin, and it's looking for the number of moles, which is great because I know I can find this formula. PV equals nRT, I want to find number of moles, so I have to isolate it, right? So all I have to do is opposite function, opposite side. It's on the right-hand side on the multiplied by RT. I have to bring it to the left-hand side and divide by RT. So there's my formula. Then all I have to do is plug it in. And our calculator gives us the answer. The final answer then is 1.62 moles. So there's 1.62 moles of nitrogen gas in the cylinder. So here's another bit of practice. Predict the volume. So now I'm looking for volume. And remember, the volume is going to be in liters occupied by 0.78 grams of hydrogen. We know that hydrogen is a diatomic element at 22 degrees Celsius and 125 kPa. The kPa tells us it's 8.314, right? We're looking for volume. We changed our temperature. We're using the 8.314. Now, we can't use mass, but we can find the number of moles, and then we can use the number of moles and plug it into our formula. So to find number of moles, we have our mass of hydrogen, okay, and here's our molar mass of hydrogen. The grams cancel out, and I get my answer in moles. Do not, and here's another thing, kiddos, do not round all the way through. You just round one time, and it's at the very, very end. So keep your numbers, keep the integrity of your numbers until the very end. So now that we have our number of moles, we can go ahead and use our PV equals nRT. Remember, trying to get rid of the P, right? So it's going to go down to the bottom to find our new formula. Once you have your new formula, once you've manipulated it, you just plug in your numbers. The only thing you have to keep in mind, remember, temperatures in Kelvin, and your R value depends on the pressure, which is kilopascals. So our volume here is 7.573. We'll round that off to 7.6 liters. Always in liters. Unless I ask you for milliliters, your answer will be in liters, and then you have to convert. All right, let's just go ahead and review real versus ideal gases, because this is really important. This is very important. A real gas is a gaseous compound that really exists in the environment. So it really actually exists. An ideal gas is hypothetical, and it does not actually exist. There are intermolecular attraction forces, right? Intermolecular forces that are in play that will cause gases to be attracted to each other. In an ideal gas, no intermolecular attractions. The particles have a definite volume and a definite mass. In an ideal gas, they do not have a definite volume, nor do they have a definite mass. Collisions between real gas molecules are non-elastic, where these are elastic. And also here for collisions, it does actually cause the gas particle to deform. Kinetic energy of real gas particles is changed with collisions. Kinetic energy, right? The more collisions, the higher the kinetic energy. Kinetic energy of ideal gas particles is constant. Nothing changes that. A real gas may behave as an ideal gas at low pressure and high temperature conditions. And an ideal gas, if you take the concept of an ideal gas and you subject it to high pressure and low temperatures, it may start, in theory, it may start acting more real. But ideal gases, remember, don't exist. They just are a theory. So if you want to try some extra homework, go ahead, and there's the ideal gas practice found at the end of the note package. Have a good day, kiddos.